I think we can start this panel section.
Okay, yeah, I'm here. What's up?
Okay, welcome everybody to this panel section on discrete versus continuum or continuum versus discrete approaches. And the main question will be eventually if the spacetime is discrete, in which sense is discrete, depending on the theory that is proposed by, in this case, by the panelists. And we have the honor to have here Professor Dvali, Professor Lewandowski online, I guess, and Professor Rachwał, Professor Surya, and Professor Woodard. So let me give a short introduction in which I will present mainly what I understand about several approaches to quantum gravity in 4 slides. And later, after my comments and the slides with questions, you can expand, figure out if there are mistakes in what I said, and so on. So first of all, even for the younger students, I would like to mention what was historically the main problem in quantum gravity. So the main problem was that all the fundamental interactions for particle physics are at the quantum level described by renormalizable theories. However, Einstein's gravity is not renormalizable. And in some sense is similar to the Fermi theory for the weak interactions. And in some approaches that I will mention later, this is exactly what has been done in the past. So to replace Einstein's theory with something else that has good properties at quantum level. Good means renormalizability, or something else for other people. Anyway, in general, we have many proposals, actually, maybe too much, maybe no, I don't know, maybe too many. And today, I guess, the expertise probably will know more about quantum gravity and the approaches proposed historically. But mainly, I think we will discuss continuum theories, theories that are fundamentally continuum. Is very difficult to say if it's discrete or continuum. We will see in a moment what I mean, or what I think is the right definition. So we have string theory and quantum field theory that I would say are continuum approaches, but also other approaches like quantum gravity or causal sets that are more intrinsically and fundamentally discrete. But next speakers will expand on that. About quantum field theory, like I said, usually what people did in the past and also recently is to go beyond Einstein's theory, so to add other operators and likely to get a theory that now is consistent with renormalizability and hopefully together with unitarity. Exactly like for the Fermi theory. There is an approach which is perturbative, but also an approach which is non-perturbative, and if they are both correct, somehow they have to merge together in the end. But that's my point of view, of course. Also, regardless of the theory that people propose or people like, others more investigated infrared modifications supposed to be effective models for quantum gravity, and also, but mainly to explain some observations like the cosmological acceleration. This is what I think it should be by the quantum field theory framework. However, and this is fundamentally continuum. So you use, by fundamentally continuum, I mean the usual quantization procedure, right? You have your momentum, your coordinate, and you quantize. And that's what you get. String theory, I think, is also fundamentally continuum. Exactly in the same way. It's very similar to quantum field theory. In short, you could say it's a two-dimensional theory, but and the theory in the space-time is emergent. It is supposed to be finite theory, so solves the initial normalizability problem and goes beyond with finiteness, and mainly because there is the large symmetry, nice large symmetry, which is modular invariance technically. Although there are some issues maybe, but the speakers know more than me about that, on defining the modular superspace. As I said, it's fundamentally continuum approach. The quantization is you take X, the conjugate momentum, you quantize, and you get everything. You also here see discreteness. The spectrum is discrete, but that's not intrinsically due to the approach, because it's like the harmonic oscillator. It's not intrinsically continuum in the procedure, in the Dirac procedure. It's just a result. Some operators are discrete, some are continuum, and there's a continuous spectrum, so far like for the hydrogenator. The entropy turns out to be discrete, as far as I know, as far as I understand, in string theory. And let's now pass to other approaches like quantum gravity, which is now instead fundamentally discrete. As far as I know, as far as I remember, because I worked on it in the past, mainly, first of all, is claimed to be a non-perturbative approach, and I think it is. But what you really do, maybe Professor Lewandowski will comment on this later, you don't make the usual quantization. It's topologically different quantization. It's like to quantize not directly the momentum, but directly the translation. So it's really intrinsically, as far as I understand, discrete. There are also here implications, but this is not the main thing, I guess, about the question we would like to answer to, which is the area discreteness spectrum, or similarly for the 3-volume, but not for the 4-volume, and other operators at length at this time. It's tricky here to see why the theory should be finite. So to answer the question of normalizability or finiteness, but it's a mix of this quantization procedure, which is discrete, but actually diffeomorphism invariance help you in making the theory fully finite. There are other approaches like spin foam beyond group quantum gravity or group field theory, but these theories go beyond Einstein's theory. So in a sense, it's not anymore the direct quantization of Einstein's theory, which is supposed to be normal. Finally, for today, there is an even more fundamentally discrete approach, which is Caldas set, in which I'm honestly not that expert on the topic, but here really you start from a mathematical axioms, and you impose some causal ordering between the events, and the space-time turns out to be emergent. So here I have a naive question, for example, if in comparison to the other approaches, usually you have a classical theory, you quantize it. Here you have already the space-time, you have a different recipe, and the question could be, I have to, afterwards, to quantize eventually an effective theory that emerges from space-time, or is already the final answer we are looking for. Finally, here are some questions, maybe naive, maybe incomplete. Of course, the list is going complete. That the referee, the panelists later can try to provide their point of view, their comments, and eventually to correct my mistakes in this short presentation. So now, after this short introduction, I would like to invite any panelist to give his point of view about his proposal on with or without eventually a few slides. And because of the order here that I got from the organizers, maybe I can invite for the first Professor Dvali. Say something.
Yes, it's alphabetical.
Yeah, should be.
No, any other problems, just alphabetical.
Yeah, okay, so actually, probably I should be the last one because I never worked on discrete, anything discrete, I mean, regarding space-time, but But yeah, I can say a few words. I mean, I'm mostly here to try to educate myself because I have a few questions about this as a continuum person coming from the continuum. And so these will be my questions. So in gravity, right? So the issue is well, as you said, non-renormalizability, but usually the issue with non-renormalizability is that the theory has a cutoff, and we want to have some computational power once you reach the cutoff scale. We can do perfectly nice quantum computations below the cutoff. Like as you said, Fermi theory is perfectly quantum. There's no problem. I mean, for chiral Lagrangians. So now when we come usually with some big ideas, like let's say discreteness of space-time, etc. So usually these ideas are of two types. So one is when idea solves some existing problem in the framework, but there are also some what-if type of ideas. I mean, the idea may not be solving anything, but it's spectacular. So you say, why not what if? So now this would be my first question. I'm trying to understand whether discreteness concept is what if type of concept or whether it really solves some issue of effective field theory. And so here the question is connected with black holes, for instance, right? Because in Einstein gravity, we have this intrinsic length. And from that point of view, string theory is not any different. Because string theory just makes a little bit window between this length and the string scale. So string theory starts making things earlier. I mean, but from that point of view, there is no difference. So therefore, if we take, let's call it pure gravity, so we have this Planck length, and if we do scattering experiment, we cannot really probe distances. Not only we cannot probe, we don't even know how to formulate the statement, what it means to probe distances shorter than the Planck length. And the reason for that is that in the scattering experiment, we usually say that we probe short distances when the momentum transfer between particles, the de Broglie wavelength of the momentum transfer is shorter than that distance. And that is not possible in gravity because of black holes. Because what happens is that if we try to make collisions at very high center of mass energy, the theory classicalizes by unitarizing itself by multi-particle states. So instead of making collision between a very energetic hard quanta, it creates many soft quanta. And so the momentum transfer per particle always goes down. And in semi-classically, this is viewed as a black hole production. So basically what you do, you produce big black holes. And so then the question is, okay, now if I assume that there is a discreteness length in the theory, by the way, I can understand what it means emergent space, at least that I can visualize. I have no idea what it means emergent time. That's another thing I would like to learn, what it means that you don't have time and then all of a sudden in effective theory you have time. That would be fantastic.
After some time.
No, sorry?
After
some time you get time, exactly. So that would be fantastic.
Yes.
Yeah, thanks for the nice comment. And yeah, so you see, one question would be like that for a naive person like me. If I introduce a discreteness length, if it is larger than the Planck length or larger than the string length, then it's not needed because nothing special is happening at distances larger than the Planck length or string length. If it's shorter than the Planck length or a string length, then it's not really, again, it's sort of hidden. It's not. And so this would be very interesting to understand. I mean, what are we solving any problem with this discreteness, or it's what if type of a problem? So if it's what if, I mean, absolutely, it could be that indeed space-time is discrete. I mean, nature, we cannot tell nature how to behave, but okay, so this would be the question. So probably
one question to understand better. Do you mean that you need another theory beyond Einstein's gravity because of the self-completion, etc., or is Einstein's theory will be sufficient if You
Yeah,
use this concept.
yeah, thanks for so when we say that indeed, I mean it's so indeed it's a very good question. What does it mean theory to be sufficient or not, right? So in other words, like in QCD, let's take QCD, right? In QCD we have a strong coupling scale, and there is nothing we can do about it. That's an experimental fact. We know that there are degrees of freedom like gluons and quarks. They work at short distances. There are degrees of freedom that work at large distances like pions. And when the two descriptions meet, there is a strong coupling. And we have to live with it, and we live with it. We somehow try to do lattice computations, this and that. So it could be that in gravity, the situation is like that. So you have a strong coupling at one scale, for example, Planck scale. By the way, string theory doesn't change that story. In string theory also, the very high energy, the center of mass energy collisions again are dominated by black holes. What string theory advantage of
people say that is soft string theory in the UV, right?
yeah, exactly, like gravity. It's the same thing. So in fact, the amplitude computations in string theory explicitly show that if the center of mass energy is very high and the impact parameter is larger than the string length, you recover effective field theory computation. Even the exact string computation recovers effective field theory computation. So from that point of view, they're not very different. Of course, string theory has other beautiful properties that it offers unification, because it offers unifications of different spins in a beautiful way, because you have a string and its vibrations and so on. And it offers the way to compute loops in the perturbative series. So of course, it has other advantages, but what I meant, like, as far as the minimal length is concerned, from that point of view, Einstein's gravity and string theory, they are the same. They both tell you that there is some sort of a minimal length, and beyond that, you cannot probe it because it's shielded by soft physics, as you said. Okay, and so yeah. So
okay, thank you very much. So we can ask now to Jerzy actually what he thinks about my comments, but in particular the comments of GitHub.
So for me, general relativity is first of all diffeomorphism invariant, and this diffeomorphism invariance is something which I think causes this discreteness. To give you an example, if we consider a function, then, well, certainly function describes local degrees of freedom. At every point, it takes some value. But if we want to describe diffeomorphism invariant properties of function, then actually we'll end up, well, maybe maximum is a diffeomorphism invariant concept, a minimum, and etc. But then we end up with a list of some countable list of properties. So when we quotient by diffeomorphisms, then we are left with some discrete set of data. So I in my work on quantum gravity, this was my impression that the reason why we see this discreteness is exactly because of quotienting by diffeomorphisms. But on the other hand, having said this, I have to confess that if we introduce sufficiently, if we introduce more degrees of freedom, I mean, if we couple, so this is all true for vacuum gravity. But if we add matter fields, then actually we can again have continuum, because, well, it's if we introduce 4 scalar matter fields additionally, then they can serve themselves as an extra spacetime. So we can think we have 2 spacetimes, one our spacetime, and the other is this set of 4 values in which the scalar fields take values, and then when we quotient, then at the end of the day we are left with a single 4-dimensional object. So the conclusion is that maybe that discreteness happens when we just think too much about vacuum gravity, and if we don't bring in sufficiently much matter. But maybe if we from the beginning, if we consider gravity and matter fields, then maybe due to then maybe we will not see discreteness at all. Maybe if those matter fields are somehow from the beginning considered as fundamental for construction of quantum theory. But this is just a guess. I'm not 100% sure. On the other hand, we have models of loop quantum gravity, as I mentioned in my talk, coupled to 4 scalar fields, and then actually we end up. Then the result is that vector constraint and scalar constraint, they are actually not anymore gauge transformations because we solved those constraints. So we again have some space-time, but then in this space-time diffeomorphisms are symmetries. They are not gauge transformations which we should which don't represent physical degrees of freedom. Then this every point of this space-time indeed is a different point. So yeah, so this is as much as discreteness versus continuum is considered. However, still, if we consider loop quantum gravity coupled to 4 scalar fields, and if we swallow those fields and then diffeomorphisms become really symmetries and of theory rather than gauge transformations, then still we have this old framework which I presented today. So then this Hilbert space defined by holonomies and by parallel transports and by fluxes, it works, and those operators work. Perhaps the only restriction is that we have to consider observables, and observables should be diffeomorphism invariant. So we cannot really consider volume of some small region. We should consider a volume of the whole thing. So the total 3-dimensional volume. So perhaps then again we are getting a little. I mean, we lose some degrees of freedom. So our observables cannot be defined at a point. They are they should be diffeomorphism invariant. So one way or another, this discreteness somehow survives. And as far as loop quantum gravity is concerned, even though we are never discrete, we always consider full theory, and our observables are defined on some manifold. Then at the end of the day, the spectra of operators, they indeed are discrete. So they are discrete not because of this. We started with discretized theory, but they are discrete because they want to be discrete.
Just one comment, but do you agree that the introduction of holonomies is crucial in this approach, in order to get some, okay.
Yes, so of course, whatever we do is crucial. So yes. So of course, this if we show some property, then usually it follows from the assumptions we made at the beginning of our construction. So, but holonomies are also okay. Each holonomy itself is a little discrete notion because it is. But actually, why do you think that
no, I don't
holonomy is discreteness? Yeah, I agree with you, but I just want to have some good reason why I agree.
Well, one thing is to quantize an operator which has a continuum spectrum like momentum. The other thing is to quantize the translation operator, which is which is discrete, which makes discrete translations, right? So this is crucial in many places in this approach, I think, as far as I know, as far as I remember. So somehow it seems to me that introducing the holonomies is, from the beginning, it's like to tell the theory to be discrete fundamentally. But
yes, so what is discrete about those holonomies is relation between two curves. If we consider two curves and ask what is relation between them, then modulo, then it's true that this relation is sort of discrete because they intersect at some isolated points, or so from this point of view, you're right that you may say that discreteness is built in by restricting ourselves to functions which are functions on finite set of holonomies rather than on some continuous distribution of holonomies. We tried this with continuous distributions, but we had no idea how to define scalar products. So usually when you want to define scalar product, then you give up and you choose this discrete version.
okay.
But I agree with you. Thank you for this comment that holonomies are discrete.
Okay, thank you. Maybe we can now involve in the discussion Lesław Rachwał. And I think you have some
Yes, I have some
slides.
slides prepared.
Thank you, Jerzy.
Okay, so it's my pleasure to present something. You will, I think, immediately see on which side I am, but I will try to say something on both sides. So can you please go to the next slide, because it was just introduction. So, okay, I see better here. So about discreteness, we can have various motivations, because let's say that originally we would say, okay, we start with continuous things, and now there is this interesting idea, maybe let's try to do something discrete. The first comment that was from Sumati and also from Jerzy today morning, that we see that some operators, they have a spectrum, and in the spectrum we see discrete things. So maybe this means that, yes, we should take discrete seriously. And this example of operators, they are used, for example, in loop quantum gravity, is area or volume. It's not that the same thing we see in covariant quantum gravity, but let's say in loop quantum gravity, they take this operator, they do a work because it's not so easy to see what the spectrum, and they see the spectrum is discrete. Okay, let's assume this. Another motivation could be that we have the solutions with the gravitational theory, black holes, and we know that there's finite entropy. We have the formula with correction, but this entropy is finite. And then thermodynamical or statistical mechanics argument would tell you, okay, so it means probably that the number of degrees of freedom is finite in this table, because the entropy is finite, otherwise it would be infinite. Or in other sense, we can have the hypothesis that this gravitational field that we try to describe on a quantum level, which is not the same basically by, not all the people will agree that this is quantum geometry or quantum spacetime, but let's say that it may have some atomic structure. 200 years ago, all the people who would be doing physics would say, we believe in continuous medium. And then there was this not very famous hypothesis to do atomics. It was not basically favored. Only Einstein and other experiments, they could say, yes, atoms are real. So maybe the same thing could happen with spacetime, with gravitational spacetime. There are some atoms, different atoms. I will use the same word atoms like we use for chemistry, but of course, in the Greek sense, it was something which is indivisible. So maybe there's something indivisible exists also of finite size for gravitational spacetime. Another argument, you can count the number of degrees of freedom in observable universe. You take the volume of the Planck phase space and you do this estimation. I think maybe your number was similar, but I have a slightly bigger, and this number is finite. It's not infinite. So maybe it means that we have finite many degrees of freedom at our disposal, and what we should do, maybe quantum mechanics of this size of matrix. And this is like a qubit, but Q is equal to 10 to the 19 here, maybe, because we have finitely many degrees of freedom. So another thing that we should understand in physics, we do finite number of measurements. Whatever you take in the past, whatever you will do in the future, we will never know infinite number from our experimentalist friends. Always this will be a finite thing. So maybe it also means that something is discrete, and when we use these matrices which are of infinitely hugely stupid size. So this is something that you can view as a motivation, but I can also say that, as also Sumati was saying today, and maybe I would like that this discrete approach, they can work for us also as a technical tool that they can be used for the regularization. We have some problems like with divergences, maybe with anomalies in continuous field theories. Now we use this, and this is regulated. Okay, then of course there could be some problems. And then it's not just that there's one approach, we have many, because it's mentioned here like many approaches to quantum gravity, like causal sets, causal dynamical triangulation, loop quantum gravity, spin foams. In some way or the other, in all of them, we see something discrete. And then, okay, it's very vague, but I can say something to create like we have lattice QCD, maybe something with more restrictions and more refinement could be like lattice quantum gravity. So this was the slide of motivation. Can you please go to the next one? But there are also potential problems. So something that I may like and I may face, that my understanding is very simple, but maybe there are some problems. Because yes, when you try to do this, naively, you can have problems with diffeomorphism Lorentz. If you do kind of very brute force cutting the space-time and not caring so much about symmetries, you will lose this. I would say this is kind of inevitable, that you will lose Lorentz symmetry and you will lose diffeomorphism if you don't pay enough care. That's what I said. And then another thing is that, you know, if you accept this idea that something is discrete, then we have to go back to the IR physics, which we know is good and continuum. And as we see from the models, you are struggling a lot. And also in loop quantum gravity, they are struggling a lot. It's not so natural to recover the smooth continuous UV physics. I mean, IR physics in a continuum limits. So this is not automatic. It's not granted. So, you know, you try to put discreteness and then you maybe lose something. So this is not a good thing. And the one thing I was previously saying about the operator, but we have to remember, because now we do modern quantum mechanics, not old quantum theory. In old times, quantization was discretization. It was equality. Like you take the Bohr atom and this is discretization. But we know it's not how the quantum mechanics really works, because the example of hydrogen atom. You take this Hamiltonian of the hydrogen atom, non-relativistic, what you see, part of the spectrum is discrete, part is continuous. And you cannot say that the continuous part is not a result of quantum. It is a result of quantization. So you can also say that continuous spectrum is a result of quantization. So it's not the same thing. Discretization is not equal to quantization. In some cases, it implies, but you have to remember that we use quantum mechanics, not just discretization. We don't have to discretize quantum. We don't have to discretize gravitation. Our goal, I think, of all the people here is try to understand more about how to quantize gravity, not just to discretize. Yeah. So this is something what I can put as a potential problem. And then there was this analogy with QCD, that we can put it on a lattice, and this is a good theoretical tool, for example, to compute masses of the mesons, but we don't have to. It is still called QCD, can be viewed as a continuous field theory, quantum continuous field theory, and lattice is not a fundamental thing, it's rather a tool that we use. At least this is my approach, that here lattice QCD is just a way of regularizing things, but it's not fundamental necessity there to do like that. And another kind of response to the previous argument that I showed on a previous slide, when we have this finite entropy of the black hole, you can come back again to the problem of the black body and electromagnetic field in a cavity, and you see the quantum electromagnetic field is there, the cavity is finite volume, and you still have the finite entropy of the photon gas. So, but this doesn't mean that anything of the electromagnetic nature is discrete. It's true that the electromagnetic field should be quantized, but it's not true that it has to be discretized in a sense of discretizing quantum field theory. So in this sense, we have in the example of QED, we don't have example of new atoms. In a sense, quantum electromagnetic field doesn't have to be discretized. It is continuous all the way how we understand QED. And how we understand QED, there are no new atoms. In a sense, discrete fluctuations of electromagnetic field. So that's what we can say about the electromagnetic field. And experimentally, so far, we don't have any verification. This will be also important for the last part, that we don't have any experimental verifications that they are really new atoms, which would be kind of emerging because of some very specific form of the interaction. So we don't see this discrete or this atomicity for the gravitation, of course, probably because it's a Planck scale suppressed. And finally, there is a kind of question because, okay, I could use all these discrete things, but we can ask ourselves, but why do we still, for example, use continuous Maxwell equations? Why all these things were saying that we could discretize this and discretize that, but you see, there is some argument is maybe of more philosophical origin why we still use continuous things. So can we go next? So for the continuous field theory approach, I can mention some advantages because at least this is something that I've been working on. It doesn't have problems with this diffeomorphism violation of Lorentz invariance if you try and if you quantize, for example, in covariant way. And there exist some examples of good quantum field theories for which we don't need explicit cutoffs, so they are UV complete. And for example, there are models of asymptotic safety or UV finite. There are quantum gravitational theories of those which also have conformal symmetry, and there we don't see any discrete structure emerging. We can do computation until the end. We never have to assume because we can remove this UV cutoff up to infinity, and we never see that there is something like discreteness arising. So if we don't have any experimental verification, we can use this Occam razor. Why to complicate our life and why to introduce this such structure like discrete? It's maybe just a theoretical tool, but Occam razor would say not complicate your life too much. And my perspective was that already I was very happy in continuous field theory, so why to do something and try to, at least in my perspective, try to complicate life and start doing things with discrete? Because unfortunately, what I have understood today from the Jerzy talk and also from Sumati, at least my perspective is that, sorry, this is complication. This doesn't look like a very simple discrete model that still continuous field theory, in my perspective, looks much simpler. Of course, this is very objective. And let me just put this analogy that 200 years ago, people were doing continuous media theory. And basically, as far as we know all about the particle physics, standard model still works the same way, but it's just a quantum field theory. It cannot be just classical. It must be quantum, but it's still working like a continuous medium theory. And 200 years, people could forget and didn't think so much about atoms. And this is more or less the state that there are no new atoms here for the interactions, including also gravity. And finally, if we have, and with Leonardo, we have some model here of renormalizable UV finite and unitary quantum field theory of gravitational interactions. And also you can put maybe examples from asymptotic safety. And if this is everything what we want from quantum theory of gravitational field, then why we have to do something with discreteness? It's another question why to look for the space-time discreteness, but maybe the goal here would be just to find a quantum field theory of gravitational interactions which satisfies this, let's say, principle or this wish list. So this kind of thing about checking the space-time discreteness is something additional. It might be there, but it's not on this wish list that I said we want quantum field theory of gravitational interactions, and then it has to be, it is a very bold wish list that it has to be renormalizable, UV finite, unitary. Typically, not all these things work. So the last part, please. And then we can stay with some questions which are more related to observational physics, because if there is really this idea that discreteness, fundamental discreteness is there, not just a technical tool, but fundamental discreteness, do we have some signal about this and how to view it? We expect it probably around the Planck scale. So the question is maybe like the quantum gravity phenomenology, how to properly distinguish that signal and how to interpret. And then another question, I said that all the considerations that we saw today morning, they look quite complicated to me, maybe because I don't know almost anything about discrete geometry or combinatorics there. But can we, if this is really satisfied that we can have in a future experimental verification, can this be kind of described in some simplified models that you can get from causal sets or causal dynamical triangulation or loop quantum gravity? Because what we have so far looks, at least to me, quite complicated. So I think this is my point of view, and thanks for your attention.
Okay, thank you, Leslie. We touched many things. So I think now it's time to ask maybe who is
I think I have a
more
load
involved.
of
Sorry,
questions.
chat, yeah?
Yeah.
Richard has also.
But I think I'm next.
No,
Yes.
or maybe Sumati, yes,
Yes.
sorry, maybe I mixed the order.
It's
Sorry.
an ordering,
Just
there's an ordering
say
and
it, continuum and
there's a total ordering on the list of alphabets.
It's okay. No, and the other proper.
Right. So I have a lot of questions to answer because it seems like me and Jurek and maybe more to me because I really do think of things and I have a yes, very clear yes to my answer to this. So I will take on the load of all the questions, but I'm not sure I can answer all of them in a finite time or have answers to everything, obviously. So here's my take, and that's this lovely quote due to Mark Katz, who's a mathematician. Py is discretized. Okay, so apart from that, I think there are many reasons. I come from the tradition of general relativity rather than field theory, and I think that also pretty much describes a lot of the non-perturbative approaches. One is the effective field theory comes from quantum field theory, where one is used to certain assumptions about spacetime, flat spacetime. And when you come from the general relativity point of view, perhaps there are different approaches. And so a lot of the non-perturbative approaches come from that perspective to try to really ask questions about what does spacetime look like in the small, and do we have models? So CDTs, spin forms, loop quantum gravity. These are attempts to try to get some more fundamental picture of spacetime. I think string theory also. And so the question is what is that fundamental structure? So I told you everything I know about causal sets in the mornings. I don't want to repeat anything. But I think one of the motivations for me to look at the post-set structure of spacetime as being fundamental is because it comes from Lorentzian gravity. Just Lorentzian spacetimes have the structure. And I tried to explain this in the morning, that there is a fundamental poset structure which no other signature spacetime has. It's a mathematical structure. You can say it just happens to be that. It doesn't matter. It's just, on the side. But in fact, it contains everything apart from the conformal information about the spacetime. This is a mathematical theorem. I think that's powerful enough for me to say, why not? As Jerzy said, why are we doing this? Why not? It's enough for me to say that maybe this is the truly Lorentzian way to think about spacetime, because everything else is pseudo-Riemannian. And that was because we had to make sense of distances which were not distances. And we have to make sense of all of that because we think in Riemannian terms. There are no distances in the strict sense of a definition of a distance in a Lorentzian space. Mathematicians hate Lorentzian spaces for this reason, because distances don't work unless they have new tools to think about it. And they do, and I would say in the last 10 years, Lorentzian geometry itself as a mathematical area of research has progressed a lot. So this is why I think the poset structure is interesting. And then we have the missing conformal factor, so then put it back in through discretization. So discretization is a way to bring everything out of the spacetime out, except for the continuum, of course, because you're putting in that condition. But now you have the continuum as, like you said, like media and, whatever, various medium, fluids. It's an emergent property. And that's a picture that I think it's nice enough for me to want to work with. Now, it may be completely wrong. All of us are doing things that could be potentially wrong. And I think what I like about it, you could say it's just a tool, or you could say it's just convenient that it's all finite. But I think having it finite, having to sum over finite things is a nice property. And let me just say, okay, so what I think of as problems with the continuum. So I've also worked, I started off working in quantum gravity with continuum, in the continuum picture, in fact, things to do with with Hamiltonian approaches. And there, the idea, and I think it came up yesterday in the context of our discussion yesterday, that the idea of space-time forms that you have now, topology is space-time structure at scales that are just arbitrarily small, right? I mean, forget Planck scale, you can have it at any scale whatsoever, right? If you wanted to sum over manifolds and topologies, you could have scales, where the volume is 10 to the minus 2000 of the Planck scale. And that structure is still going to count in the continuum. So you can say, well, I'm going to ignore that. I'm going to flatten out space-time below some scale. And this is, in fact, what you do even in, requiring nice properties of your vacuum. You make it Hadamard. You say, everything's going to look flat below a certain scale. You don't really, it's not compatible with structure, which is going on and on and on at smaller and smaller scales. So I think, to me, that just feels like an absurd amount of information that you could have within a Planck scale. I mean, within a Planck scale, if I'm going to be summing over all possible topologies, all possible everything in there, there's too much structure. So it feels actually the opposite. It feels like you're burdening yourself with all of that information, which is, to me, not physical. And I've already said something about the Hadamard condition. I'm wondering if it's also true of asymptotic safety, but then maybe not, because we had this discussion whether continuum is important there or not. But the fact that you want something that sort of flattens out in its complexity after you get to a certain scale, I think that's something we desire from our theories, whether we have some kind of cutoff or not. And again, something you said many things in favor of discreteness. You were on my side for a part of the talk. So, so black hole area, units of, and then entanglement entropy, all of these things we can calculate for causal sets. It's actually not so difficult. It may be new, but to somebody who's used to doing quantum field theory, but in fact, many ways, many of the things are very simple. Otherwise, I wouldn't be doing it. So the idea also of too much topology, too many differentiable structures, too much of information in the continuum. If you wanted to take the continuum as a quantum theory of gravity absolutely seriously, in which case I can't see why you would not want to take all possible prime decompositions of a three-manifold, which means that you have really a huge amount of information. When you get to four manifolds, you have to look at all possible differentiable structures. And it may not matter for an effective field theory, and it will not matter. But if you're going to ask what is quantum gravity, what is the nature of space-time, and you don't look at all these structures, it feels to me that you're either going to ignore it, in which case you may as well have a cutoff. So there is discrete form due to fluctuations at the discreteness scale and causal sets. It's UV finite. I mean, you can argue whether that's a real UV finiteness or, you want something else of your theory, but it's also covariantly defined cutoff. It's a space-time volume cutoff. It's completely covariantly defined. And even though it's a discretization, because we are doing it via this Poisson point process, it's Lorentz invariant. So you don't lose Lorentz invariance. And this is actually a strength of this theory. I mean, I think if we did lose it, then we'd have to be forced to go to the continuum limit, like you do in any lattice approach. So here you don't, and so you can work with the finite discretization. And then something that maybe people are not aware of or are maybe aware of but don't remember is that one of the things you can get out of this Poisson process is that for the observable universe, if you assume a kind of unimodular condition, then the volume of the observable universe is conjugate to lambda. And if you use that sort of this, this is a model building thing, then there's a fluctuation in lambda, which is inversely proportional to the fluctuation in the space-time volume of a Hubble volume. But now that fluctuation for a Poisson process goes like the square root of the volume. That's the property of the Poisson. And fluctuations go like square root n in Poisson. that's enough to give you 10 to the minus 120. And this was done before the observation. So it's a very natural number that comes out of causal set discretization, which is a lambda. And of course, here it's a fluctuation. So if you take lambda to be 0, then that fluctuation today is of this order. There are models, messy phenomenological models you can build. I don't know much about those, but where one can try to build up a more dynamical theory of a varying lambda. But that is one of the, I would say that's a fairly good reason to think that there's something here that's non-trivial. And I think there is non-locality, which can arrive at scales which are not at the Planck scale, but are at intermediate scales, which could lead to interesting physics, which could leak into physics at gut scale or something like that. These are phenomenological models which people have studied. Again, not something that I know very well, but studies of things like dark matter coming from such theories. So non-local theories, but there's no UV-IR mixing because there's a very distinct separation of scales, like in condensed matter physics. So I'll end there.
Okay, thank you.
Let's not forget Wheeler.
I will leave it for 10 seconds.
So we have still 10
Yeah.
seconds, so you can.
Okay, yeah, so Wheeler says quantum fluctuations of the metric are order 1 at the Planck scale. Wild and rapidly varying fluctuations in space-time geometry and topology of space-time form. And so very wildly varying geometry could be something that's non-geometric, right, as well. So that's sort of the idea.
When you say non-locality in this model, I remember an operator that was obtained by you, but then in CASA.
Dowker and yeah.
So I remember this operator has very, very new non-localities respect to what you usually find in quantum field theory.
Yes.
So do you think you can further quantize the theory, or that's your final answer to the effective quantum theory?
No, so I think the way that this operator was used, so it's a D'Alembert operator for the scalar field, and it basically takes in, it looks at the past of a point, and then it looks at some sort of, you have to sum over various contributions from that past, and it gives you something like a quasi-local operator in the continuum. So it isn't local, but it's quasi-local. And I think, so people have played with trying to quantize this theory, to write down propagators and so on.
Do you think we have to do that, or that's the final answer?
No. So you have to so this is a scalar field, classical scalar field sitting on top of a causal set. The causal set is just the background. And then when you do this, then you can ask, how does the propagation of a quantum field on this first quantized background, so to speak, how does it behave? And that's non-local.
Thank you. Okay, so let's now invite Woodard for your discussion.
So I seem fated always to come up towards the end because of my last name. And although I am finally writing papers with a man whose last name begins with Y, so but he's not here. So I'd like to argue against something that I'm not sure actually anybody here believes, and that is fixed discretization as a solution to the ultraviolet problem in quantum gravity. Let me be clear about that. Fixed discretization means a finite number of points on any finite volume of the initial value surface. I absolutely do not mean that in some sense you can't probe smaller distances than a certain thing, that non-perturbative effects supervene to prevent you from probing smaller distances. That's not what I mean. I don't mean that things like the area operator have discrete eigenvalues. That's not what I mean. What I mean is there really aren't any smaller separations. In other words, just to be be really brutal about it, one way to implement it would be that there's a fixed cutoff at co-moving 3 momentum equal to 2 pi over the Planck length. Okay, so that's what I mean. And that cannot solve the ultraviolet problem. It would solve the ultraviolet problem, but it can't solve the physical ultraviolet problem, which is not just to make quantum gravity effects finite, but to make them unobservably small at regimes where we know that they're unobservably small. And to really bring this into focus, I'd like to inject something that hasn't been mentioned so far, and that is the staggering expansion of the universe. If you believe in primordial inflation, which I do, and which there's very powerful evidence for, then the universe is expanded by a factor of at least e to the 120, 10 to the 52. And further, if you believe in the inflationary theory of structure formation, you believe that those effects had to be small at the beginning of inflation. So they had to be perturbatively small at the beginning of inflation. That means that the cutoff at the beginning of inflation cannot have been much higher than that amount, because if it was, they would have been big, right? So then you just do the numbers, right? The physical distance, you know, we call the scale factor because it scales things. And the physical distance started out being 10 to the minus 35 meters at the beginning of inflation. It's expanded by a factor of 10 to the 52 since then. So right now, the minimum physical distance is 10 to the 17th meters, which is, you know, about 3 parsecs, larger than the distance to Alpha Centauri. This, ladies and gentlemen, is not acceptable. And let's see, can I advance that?
Yes,
Yeah, that's what I mean. It's a cosmological version of this charming novel that George Gamow wrote about Mr. Tompkins exploring relativity, and in this case, quantum mechanics. There's a cartoon picture of him falling asleep in a boring lecture of atomic physics, and he wakes up to find himself in quantum world, where I think right there, you're seeing horses go through a double slit, and they're producing interference patterns in horses. And that's the kind of effect that occurs if you have macroscopic quantum effects. Well, if this kind of hard discretization were implemented at the beginning of the universe, then right now you would have hard quantum effects. You say, okay, well, look, I don't believe in primordial inflation. That's all just stuff that the cosmologists are doing, and I don't believe in that. Okay, fine. You have to believe in the expansion of the universe right now. It's going on right now. My country paid $1 billion to measure the Hubble parameter to within 10%, and we did. We now know it much better than 10%, and the universe is expanding right now. Okay, it's not expanding as fast as it did during inflation, but if you believe in discretization, you have to believe that if we just waited to the infinite future, it's eventually going to be impossible to swing your arms from here to here without undergoing a quantum jump, because there won't even be points in between there. That, again, maybe it's true, I don't know, but I doubt it. People will say, no, that's not what I meant. I meant discretization, but I want to add new points. Okay, well, there's problems with that. And I take a really hard-headed point of view about quantum field theory. I would say that the fundamental degrees of freedom are the values of the fields and their first derivatives, or whatever the dynamical variables are the values of the fields and the first derivatives at points. And if you have only a discrete number of points, then you have only a discrete number of those things. And if you start adding new points, then you have to tell me where you got the information to give those dynamical variables. Now, you might come back to me and say, well, don't the numerical lattice guys who do simulations of the early universe, don't they do that? Yes, they do that. What they do is to just smooth, to average the information from nearby points. So if they get a lattice and the points have drifted apart and they want to fill it in to have some better resolution, they just take average values from there to there. But that's something that we, as quantum field theorists, cannot do. Not? Well, the uncertainty principle, right? These things have to be independent quantum variables. They cannot be averaged or correlated between things. So where are you going to get that information? And wherever you get it, you might say, well, I do it in a functional integral, or I blah, 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 blah. I don't know how you do it, but however you do it, you are injecting a huge amount a staggering amount of information into the theory. This makes the black hole information paradox just insignificant, trivial, compared with the amount of information you're injecting. It would be that every degree of freedom right now, every quantum degree of freedom in our Earthbound lab, in fact, in our whole solar system, is a new degree of freedom that was just put in that didn't exist there at the beginning of inflation. Maybe you believe that. I don't know. I find that really challenging to believe that. And those are my problems with fundamental discretization.
Last video was very short, so I think
Shall I put yours lights back? Or
okay. So, yeah, you can.
if you need them,
I think it will help.
like
There are many topics we can discuss.
Sorry, but this is your bite.
Yeah,
Maybe you can put it somewhere else if you don't want to.
It's okay, actually.
But you know, there's this osmosis.
Okay, what is it, Marcus? What anything can go wrong will go.
So now it's time to eventually involve also the audience, but you can talk each other, eventually reply to the other comments or the other panelists. Yes, please.
So just to respond to, I mean, I'm almost worried to respond because I think we may differ very strongly, but I hope we can do so gently. I'm happy to
We have so
differ.
far.
Okay, so I think when you think about this, of course, this particular kind of discretization is not what one is doing in puzzle sets. You're doing a discretization which is of the space-time volume. So if any finite continuum space-time volume will have, and it's large and it's macroscopic, will have enough elements in it. Now, the worry about there being new elements coming from somewhere, that you're adding entropy, is no different from the fact that there are new space-time events being created just as we speak. And in one case, we're happy with a continuum, an LF1 continuum, but we're not happy with an LF0. That's what I don't understand. So I don't know why the addition of time as it goes on is okay from a continuum perspective, but not from a discrete perspective.
I'm not sure what you mean by new events being created as we speak.
Are they not? I'm creating them.
I would say that they're not being, maybe we're not talking about the same thing. You're talking about
New space-time points coming into being.
I don't think there are any new space-time points coming to being.
How does time, I mean, what are we, okay, so maybe we have a different perspective on the continuum
You're
itself.
talking about time, right?
Yeah, but I'm talking about the continuum.
So I
We're
would say that
progressing in time.
the spatial points are all the same, and the only thing that's happening is that the dynamical variables on the spatial points are evolving in time.
So you're saying that there's no space-time coming into being, that it's only a trajectory in our.
I would say that the spatial points are just labels, and the values that tell us physics are the values of the fields. In gravity's case, the metric evaluated on that space point, and it evolves in time, like all other things do.
But if one
And
Cauchy
no
surface
new points are created.
So let's say that at this completely unphysical moment of time, which is of course particular choice of our coordinates, we say this at time t, the space-time at this up to this point is some Cauchy hypersurface.
Good.
And now I have another time t prime, another Cauchy hypersurface, right? Which is an evolution of this into that. An entire new Cauchy surface has come into being, right? That to me is a continuum that's come into being as I think of the
If you're
space-time.
thinking about space-time, I suppose there's a certain sense in which that's true, but if you're
Yeah.
thinking about it in terms of gravity, in the context of field theory, all that's happening is that the metric tensor is just evolving from one Cauchy surface to another. There's the same number of space points as there always were, and the metric tensor's value on those space
But
points
there's-
is changing with time.
Right, but there are that's time that's happening, right? I mean, the spatial number of spatial points is the same.
Well, I think that's happening continuously too, and the
Yes,
equations say
for
that it's
sure.
happening.
That's happening continuously, but that's exactly what I'm saying. It's a continuous creation of space-time events. If I define a four-manifold, and I look at
That's not what I'm talking about. I'm talking
so
about
maybe
creation of new degrees of freedom. I would say that the degrees of freedom, I would say that, well, not in the process you mentioned, but in a process where you impose, you have a Cauchy surface that has some finite number of spatial points, and then you evolve it, and the universe does what it does, which is to expand, and you eventually get to the point where it's not even possible to move your arm from one point to another because there aren't points in between, and you say, well, I have to add some more points. Then I would say that the values of the fields and their first time derivatives at those points are new information, and you have to invent that from somewhere, and I don't see any way to do that.
right. So at least in this kind of discretization, you wouldn't have that. So because it's just, I mean, the number of points that are there are just proportional to the volume. And so if you have a macroscopic space-time volume, you have a large enough number of points. So it's the same as the space-time. So I don't see any fundamental one is a continuum, which is,
I'm not sure that that's really true. Perhaps we should let other people ask questions, but I think I would object to that.
It's directly on that point. So I think what you say is we have the expansion that is observations, trajectories of test particles. That doesn't necessarily say that the underlying space-time degrees of freedom have to expand in the same way. They provide the stage. They can behave differently. If you put a test particle on it, you get next you get test lines that exponentially diverge from each other. That doesn't necessarily tell you anything of how the space-time points themselves, the distance between the space-time points themselves changes. Doesn't have to at all.
Well, in principle, it wouldn't have to, but we know quite a bit about this expansion, right? It's very well described by an FRW geometry, and that means that the space points, the distance between two spatial coordinate points in the system, in the coordinate system, which was spatially flat, is just growing like A of t.
No, but now you make an identification of the coordinates with these dots in the space-time. At the end of the day, if you look at the Sitter space, we have a finite interacting volume that does not change in size.
If we look at, say that again, please.
So if you look at the Sitter space, the interacting wedge has a finite spatial volume. And that does not change at all.
Interacting
the Sitter horizon is a constant radius.
What I'm saying is
there's a static
I don't think I agree with that statement at all. What I'm saying is that if I evolve these points, if I evolve the fields on these points, eventually the physical distance between the fields, between those points, I'm letting you discretize the thing. By the way, I'm not discretizing it. It's the other people who want to discretize it. They discretize it, and then I'm just wanting to follow what happens to the evolution of physics on that. As the scale factor grows, I would say that the physical distance between those points grows. You're denying that.
So you assign the space-time points to a value of a coordinate system. I can give you a coordinate system in which the interacting patch is static.
The interacting patch is...
Yes. I mean, could you elaborate? Because could you elaborate what's your version of discretization of the space-time in which what Richard says doesn't happen?
All I'm saying is the argument is flawed because he attaches value to... I'm not going down on either side of it. I'm just saying arguing like that is you're saying that a certain coordinate, that the same sort of discrete representative always has to assign to the same coordinate value. Then you choose a very particular slicing of the Sitter, like if we talk the Sitter space, for example, you choose a very particular slicing and you assign a meaning to it. You don't have to. You can choose, at least for the interacting region, you can choose a different coordinate system, and then you're static, and then it's all
I don't think there's anything you can do to keep the points from experiencing space-time expansion
I mean, it's proper distance. I guess proper distance is covariant. I have no problem with that. But I'm just saying that in the kind of discretization I'm talking about, because the space-time volumes, right? I mean, I'm talking about space and time together as one object. There you have the right kind of things to look at are these Alexandrov intervals or causal diamonds, and the volumes of those are going to grow, right? I mean, the volume of de Sitter, the space-time volumes are also growing, along with the spatial volume, everything is growing. And therefore, the continuum approximation will only make sense if I have enough points that represent that expansion. So imagine if I were to take the skeleton out and I say, this is my space-time and everything is happening on that. There's no extra points coming from anywhere. This is the space-time, but it's a discretized version of space-time.
Where are the initial values for the field variables on those points that you're putting in? You're putting in more points as time goes on.
You're not putting on more points. Are you putting as many points as you have in the space-time?
This is
Per unit discretization scale. You're not putting in, if I think the entire space-time.
In that case, then I think you're up against the other situation that eventually it gets to be impossible to move your arm physically from one point to
You'll
another.
always be in the classical regime in the right, because the Planck scale is all, if you have a continuum space-time volume, which is
covariantly
defined object that is large, you will
suppose that you arrange that at the end, it is possible to move yourself continuously from one point to another over macroscopic distances, then I believe at the beginning, the physical cutoff corresponds to something that would not have made quantum gravitational effects perturbatively small.
Everything you're thinking in terms of spatial distance. You have to think in terms of space-time volumes.
You're 100% right that I am thinking in terms of spatial distances, and I
that's
think
not the discretization.
But I think that that's okay, because whatever formalism that you suggest has to be translatable in terms of perturbative formalism, where I've got three momentum integrations, and they are going to get cut off at whatever is your spatial separation.
Yeah, I don't have an answer to that.
Yeah, maybe I'm sorry. I think somewhat the question of Richard, if I can try to rephrase it, was that, and I mean, I think we can get a definite answer. On the Cauchy surface, you have different number, I mean, at different time, you have a different number of degrees of freedom or not? Because I think Richard was very worried about this fact that you get some degrees of freedom coming from wherever else, but the number of them is so big that it basically invalidates everything what we know about field theory, continuous one. So the question, you have the Cauchy surface, a different time, T1 and T2, and you say the number of degrees of freedom is the same, or it changes?
So the question is how, okay, so because it's a fundamentally discrete theory, and I've told you that you recover the continuum via Poisson point process. So you give me a codimension in surface in that, it will never, it's a set of measure zero. It can never be realized. The only way you can realize Cauchy data is by appropriately finding a coarse-grained, thickened region, okay? And that would be my effective Cauchy data. And then if I can construct, I will be able to construct something like that, which has a distance function, which has an induced metric. I have everything on it, and that will evolve to another one. But of course, this is at scales that is much bigger than the discreteness scale, that such an effective thickening happens, because at the discreteness scale, the fluctuations, that's not where you begin to ask such questions. So if you want an effective theory, you've got to do the right kind of coarse graining of this structure. If you go to the discreteness scale and ask for structure at that scale, you're not going to get it. But then, that's the wrong thing to do in the first place.
But let me say, I mean, just
it's like going to the atomic structure under the table and say, show me the color. I mean, demand that you give me this color white at the atomic scale or the molecular scale, whatever. You can't get it. You have to do the right coarse graining before you get back effective descriptions of this table. I mean, I don't know how else to say it, but yes, this is the.
But do you agree?
I've gotten as hot as I can.
That there will be some corrections, maybe still suppressed, but there will be some corrections. Yeah,
sure, there will be.
And then you see, looking at the numbers, the figures that Richard showed to us, I still can be worried because even if this correction you say 10 to the minus 20, Richard can multiply by factor whatever 10, and when you can
52.
Yeah, so Richard can multiply by 10 to the 52, and still this is a big effect. I mean,
And from now
it's like saying that it's like asking the following question, even in the continuum.
but can you?
In the continuum, at time t equal to 0, if you have compact hypersurfaces of volume, total volume V1, suddenly you get, at a later time, compact volume V2, which is much, much larger. Where did that information come from? It's literally the same thing. One is, in fact, worse than the other, because in one case you have a continuum of information, and in the other case you have a LF0, a countable infinity. So I think we're talking about the same situation where you cannot look at GR and say, where does that information come from? Where are these new degrees of freedom? Your space-time has suddenly expanded. Where did that information come from? It's the same thing. It's no different.
Well, I think you're fundamentally denying my way of viewing things. You insist that the only sense that I can make of physics is a functional integral over space-time, and I'm instead insisting that we should be able to talk about physics as being defined on some Cauchy surface evolving into the future. And you are
No, I'm going to say
you're not saying that, right?
no. I think so. If I'm going to talk about Cauchy hypersurfaces,
Yes.
I have to coarse grain my spatial whatever I think of as a fundamental structure, because at the scale,
Yes, no, I think you,
there is a coarse grained version of a Cauchy hypersurface which has all the information.
but I think you did agree then with what I was saying. So I think the fundamental dispute between us is that you insist that the only correct way, the only fundamental correct way to view it, that has everything present in it, is as a functional integral over space and time, whereas I would say that that's just a particular way of calculating an in-out amplitude, and that the thing that defines the fundamental theory is the P's and Q's of the dynamical variables on the initial value surface. And I think we fundamentally disagree about that.
I mean, at a fundamental level, yes, but I think effectively you could definitely construct something like this out of a.
And I think I would go further and say that this business of coarse graining and everything that you're doing at different Cauchy surfaces is, by my standards, putting in new information as you go, as you would go from one Cauchy surface to another that you define by coarse graining. And you, I think, are not sensitive to that as a problem, but that bothers me quite a bit.
So I think of it as the same. I mean, so I'll reiterate that a space-time that's growing in its spatial volume is what you could also say that you're getting information from somewhere. You could just say, oh, but then you're getting more space. Where's it coming from? It's the same way. But the question is really, I think it's from that.
It was always there.
So I also say it's always there.
Some huge issues.
I also say it's always there, except that space-time that you're viewing is always there.
You know, maybe I'm misinterpreting what you're saying, but I really think you're not saying it's always there, because you're saying that there's just a fundamental finite number of space-time points. It's even worse than for me.
No.
I would have continuous. I would allow you to have continuous time, but finite numbers of space points. You're actually discretizing in space and time.
But that doesn't make it fine. It's a countable infinity. It's a countable infinity.
Let's put it on a finite volume so we don't have
spatial volume, but not in time. You can go as far as you want in time.
Okay, let's. It seems to me that might
follow up.
Okay.
Yeah.
So yeah.
Yeah, so I have difficulties following the arguments both on the discrete and the continuum side. You seem to, at least correct me here, to assume that space-time is like a substance, something which exists in itself. You can point at that space-time point or the space point, that's point, and say that they diverge and that they are little of them. I thought that relativity has taught us that space-time is irrelevant, really, and the only thing that is important is relationships between fields. The metric field being the most important one, but of course also matter fields, so that the space-time continuum or discrete, whatever, is just scaffolding that we use to build our mathematics, which assumes fields on something and we provide something, but then when we extract the physics, we take away something because it's not relevant. It's only the relationships that are relevant. That's particular. So your argument seems to me, and please do correct me, that you assume that space-time points in a discrete version that you criticize are actually exist and can move with respect to each other and can be diluted in some way.
Oh no, I'm assuming that there's just some finite number of them, and that finite number of them is chosen so that so I completely agree with your statement that the only thing that matters is the values of the point of the fields on the points, and then the only issue is, are there finite numbers of spatial points or are there not? And if there are, and see, I would say that the points or the spatial points are just labels that characterize which fields we've got. And the only thing that matters is what the values of the fields are. If we look at what the sort of average value of the universe is, then observation tells us that it's expanded by this staggering amount. And that means that if we chose the discretization so that, again, in terms of the values of the fields at the time, that quantum gravitational effects were small at the beginning of inflation, which data again is telling us must be true, then right now it wouldn't even be possible to move your arm continuously from one point to another. In fact, you couldn't even go from the Earth to the Moon continuously. You'd have to take a quantum jump to go from here to the nearest star. Because there wouldn't be any space points in between, again, measured in terms of the physical distances at the time.
That still sounds to me that there is something in between which isn't in between. When you go from, you say that they say one point and the other point is next point is there. Okay, then that's the physics if you don't have that. So
but see, that's bad, I would say, right?
Can I?
Yeah, I think the only thing your argument shows is that space-time substantiveness and this.
I'm sorry, the what?
That substance, that space-time as a substance is a weird way of thinking about space-time. That's my take from your argument.
But I'm agreeing with you. I'm saying that the thing that matters is the values of the dynamical variables on the coordinates, which I take to be just labels.
Points.
So there's one label that's us. There's another label that's the nearest star, and there isn't anything in between.
But there's no label on the space-time points.
I'm sorry.
Never mind.
Maybe there is a follow-up.
Yeah, I just wanted to maybe a little bit clarify your point. I mean, I fully agree that, of course, in quantum field theory, the fields are the dynamical variables, and space, at least space, time, okay, time, but at least space is a label for the fields, and so but and I understand what you are saying. You are saying if the cosmology there is like envisages that you create universe in a finite number of those points, and they stretch, but we were not told how they envisage cosmology in this frame. So you said that? What was?
I'm just kidding you. I mean, I don't know how else to do it except show a diagram of.
Maybe my question can help. I just want to say so. Your idea is that okay. I'm not defending discreteness of space-time or anything like that, but I mean, if you because you brought this example of a table, I can think of it as an infinite table from the beginning. Yeah. And then what is red shifting? Are some fields that are fluctuating on this table.
That's fine, yeah.
And that could create the illusion of the expansion. Is that because in that case this problem would not arise that you are saying. So you are not stretching really the table. You are shifting the phonons on the table, but
yeah, I mean,
would that be the way you?
Well, no, there's always
space-time here, like basically that if you have n amount of atoms here, and this is not how we think about it, because we think about it from the point of view of the space-time. But suppose you were to say that the
this
volume.
Is a poor man's version of
thinking.
Yeah.
That's good.
Right.
One table, this table is smaller than that table. This has fewer atoms than that. And already in the continuum, you're telling me that you can go from this to that as a continuum object, right? The space-time is evolving from this size to that size.
I meant slightly different. I meant that from the beginning, let me take an infinite table. So from the beginning table, it's discrete, but it's infinite.
Yeah, then you have no problem.
Yeah, that's what I'm saying. In that case, and there, the cosmic expansion could be redshift of components or whatever.
Yeah.
They expand in their wavelengths.
And the point is that
then this problem would not arise in that case.
I think it even would arise in that case if you think very carefully about it. The infinite space just obscures the issue.
It depends on how you're discretizing. And this is why I wanted to make a point that if you discretize it the way you're saying, I agree.
Okay, good.
But it's not how we discretize it. There are different ways of discretizing, and every discretization will not give you this kind of thing. In particular, I mean, if I were to just draw, I mean, you all know a de Sitter, right? I mean, let's place de Sitter, 2D de Sitter here, and how do we assign points on 2D de Sitter, right? How do we discretize it? So the way I would discretize it.
Normally don't.
Yeah. How would I discretize it? I would basically look at when you do this Poisson point process, it is uniform with respect to the space-time volume. So if you ask for, if I go from minus t to plus t in this, in this hyperboloid, then I would say that it's uniformly distributed, not with respect to the spatial volume, but with respect to the space-time volume. So if that's the case, then I know that any space-time volume, which is macroscopic, will have very large number of points. I will never be in a void. I will never be in a place where I can actually just, put my own.
But then you have a much larger number of points on the final sector.
If you make a co-moving volume of certain co-moving volume.
Spatial volume.
Let's say spatial, yeah. So the number of those, whatever you call them, points or degrees of is increasing, is changing within that co-moving volume or not?
We talk in terms of the region. Yeah, I don't know. Apart from
sorry to ask this
question.
No, I know they are very naive, but no,
it's
the right questions.
Yeah, I'm just trying to imagine how this could work.
But the point of space-time points, which means that you have a relation between, so that's an event. So those points, they're not okay. So this is the difference. I think you're thinking in terms of world lines. I'm thinking in terms of space-time events. So you're thinking about lines that are going up and down.
I'm thinking about whatever are your degrees of freedom.
Because I'm thinking about space-time events, and I think that's the fundamental thing. But let you like.
I think you agree that just short comment that this event will
Let's ask because there is also this difficulty.
So Richard made me think in what way my loop quantum gravity universe can expand. So from loop quantum gravity, it would look in such a way that I can choose some region of space like this room in which you are guys sitting, and then there is an observable, which is just the volume of three-dimensional volume of this room. Okay, so on one hand we have observables, on the other hand we have quantum states. So my observable is sort of fixed; it is this room, and then and then my state is evolving. At the beginning, there are a few vertices, and they contribute a very small volume. But then, as time goes on, then new and new vertices of the state appear, and each new vertex contributes a new volume. So in this way, this volume is growing. So I have no problem in growing the volume. I would rather say there is volume when there's problem when we want to increase the volume to zero. So then at some point we would have no vertex inside, or or maybe our universe would be bouncing. So this is the answer in terms of loop quantum gravity, or at least one of models where.
So are you saying you add new points, new dynamical variables as time goes on? That's not as
No. So it's not me. It's just Hamiltonian. It's just the evolution. So the state is evolving according to some Hamiltonian, and then during this evolution, at the beginning, this state is a graph which has a few vertices in this room, and as it is evolving, then it develops more and more vertices, and each new vertex contributes new volume. And also, there are those quantum numbers, so it's not only the points, the vertices, but also each vertex comes with some quantum numbers, so those numbers can also be changing.
If my knowledge is way out of date, and I confess I haven't kept up with the latest in loop quantum gravity, but as I understood it, the variables start out being the Ashtekar variables defined at space points, right? And then I would say you have an infinite number of them. You never discretize space. So I would say that you're in the situation that I ruled out right at the beginning, that I said I wasn't talking about, and that is that somebody is saying that it's just the case that
yes. I noticed this, and I appreciate. So I just wanted to, since I did this intellectual work, and I imagined this expanding universe. I answered in what way it's looking
like. I would call it continuum field theory, right? I would say so, but maybe I don't know the latest in LCG.
Okay, so now I'm not contradicting what you are saying. I'm just explaining in what way. So maybe it also explains a little the nature of discreteness of loop quantum gravity, is that indeed our states are discrete. However, our observables are not discrete.
You're
so
saying
it's correct that we have infinitely many points from the beginning.
Eigenvalues, the same way that I think Leonardo mentioned that the harmonic oscillator has discrete energy eigenvalues, but nobody would say that it's a discrete theory. The positions in continuum or position and momentum operator are continuous operators. And I think that's what loop quantum gravity.
So we agree. Thank you.
Maybe I didn't.
Yes.
Okay.
Thank you. There is, I think, one more hand raised in the Zoom auditorium.
I can comment on this thing because Bianca Dietrich was here last week and she talked about loop quantum gravity or some version thereof. And there she has something that to me sounds like this adding new points in the middle. And in her description, it's a Hilbert space that grows as time passes. You don't always have one Hilbert space, but you have a sequence of Hilbert spaces that become larger and larger as time evolves. So my question to them there, to everybody that was present, was, does it not sound like bonded theory of continuous creation? And nobody was able to answer that.
Sounds like that to me, but Jerzy's the expert.
Yeah, so there is actually confusion even between people doing loop quantum gravity. So some people, as myself, are conservative, and I consider infinite manifold and observables which are assigned to points, and only states are discrete. On the other hand, Bianca perhaps has some other version in which is more discretized, in which her Hilbert space is growing. But this is not this standard loop quantum gravity. This is some other version.
So can I ask a question, Jurek? Because so you have kinematic states, and those are on graphs, right? Which you get on graphs. So there's two questions here. First is that you solve the diffeomorphism constraints. So these are quote unquote physical states, but then you also struggle with the Hamiltonian evolution of these states, right? Because we don't quite know, at least from what I can tell you, one doesn't really know how to implement the Hamiltonian constraint to know how things evolve. So the question, I mean, in spin forms, because you revert to a more path integral approach and you're summing over all possible intervening geometries, that's how you get new vertices, or you have, so is that right? I mean, is it that in loop quantum gravity itself, you have a way of actually evolving this graph in a meaningful way over the Hamiltonian?
Okay, so what I did is I selected of all possible couplings with possible matter fields. I selected the one which is the easiest to deal with this question, which is coupling gravity with 4 scalar fields. And then when we solve the constraints with respect to those scalar fields, then actually those kinematical states of vacuum gravity, they become physical states of this, or already solutions to the constraints of this theory coupled with 4 scalar fields. And in that case, every graph is indeed a solution to is a physical state. And then there is that Hamiltonian which evolves those graphs and adds new elements to do those graphs, new edges, new vertices.
So in what, okay, so maybe the question there is that you can create, because you have associated with this also volume, so spatial volume. You can create spatial volume. So if you were to start off with a graph corresponding to volume V1, and you have and you evolve to another graph, and this is sort of like your expanding universe, to another graph which is a volume V2, would you need to, what is it that changes? What is it that your Hamiltonian does? Does it add new points, and so that you have a graph with more points or less points or the same number?
Yeah, it adds edges and vertices to this. So this graph is growing.
So in that sense, this would be similar to this growing Hilbert space in some approximate.
Well, I'm not saying it's always growing. There may be some other solutions.
Yeah, of course, yes.
When it's just changing. The graph is changing. Some elements disappear and some new elements appear.
But as I remember, the Hilbert space is defined, it's the same. So then if the theory is unitary, then creation or annihilation of points is not a problem. But
indeed, this was my actual question. What does it mean that Hilbert space changes in a theory in which you have a Hamiltonian?
The Hilbert space is done. It's done.
Yeah, Hilbert space is whatever it is.
Yeah, but if the graph like was described this morning,
the Hilbert space contains all possible graphs. So
right. So then
the Hilbert space is huge.
Otherwise, I don't know. So the Hamiltonian is fixed and Hilbert space is fixed. And then time evolution explores different regions of this Hilbert space.
Yeah, and the state might evolve.
Right.
That's okay. But the fundamental degrees of freedom are
right, exactly.
Right, and points correspond to observables. Yes. So there is. So that's why points don't evolve, because points are observables, and what is evolving are states.
Yeah.
So but this Hilbert space, when you sum over all possible graphs, is a non-separable Hilbert space.
Yes.
Right. So, I mean, there are issues also with this. So, but the point is that, okay.
What issues?
I mean, it's a non-separable Hilbert space.
So the Hilbert space changes as time goes on?
No, it's a
I think that the argument against non-separable Hilbert space is that we are never going to make sufficiently many measurements to investigate all possible states that are contained in this Hilbert space.
So maybe to change topic a bit, and now we talk a lot about personal preferences and if theoretical arguments one way or another. So as we've already heard, there's a finite amount of experiments we can ever do. Now, for the sake of this discussion, there's a key question. Is there, in this set of finite experiments, one we can do that would actually allow us to determine whether we're in a discrete or in a continuous space-time.
Let me just say, I think now we are in continuous. Yes, I can move and you don't see pixelization of my hand. That's a short answer. But I think for quantum gravity is a question first at which scale.
That's an approximation.
But at which scale? Yeah. But you see, you didn't see the pixels.
That's the point. At what scale?
There's probably two questions there, right? Because normally in physics, when we create a theory, first you need to have a working theory. And then, then this working theory may have predictions. And I think, yes, if the working theory of discrete spacetime can be constructed, then it will depend on the scale. So probably if you do measurements at that scale, you will see some effects. But I think we're on the stage one with a working theory. We're discussing whether you can have, and in which sense, a working theory of a discrete spacetime. And so without that clarity, it's very hard to make a prediction.
Yes, I mean, you have to construct the theory and you have to...
So yeah, my question was more whether like theory independent, there would be an argument, there would be an experiment one could conceive that would sort of like probe whether fundamentally, now let's suppose technology doesn't matter, but like that can fundamentally distinguish between a discrete structure and a continuous structure of spacetime, apart from any particular spacetime, just how does it fundamentally the structure behave? Can we test that?
Well,
completely.
Yes, let's assume that you can have a theory of that type consistent. This is a necessary assumption. And let's say scale is 10 to the minus 17 centimeters. Then tomorrow LHC in principle can probe it. So you should see some weird effects at LHC that you would not see in continuum theory. So now, presumably, if you ask me, should be some kind of new resonances which behave in a non-Lorentz invariant, something.
You'd see the structure function of the electron, not the point line.
Right, exactly.
That's the best measurement.
How would you test whether something is a continuous theory?
No, that's impossible to test without the theory.
You could only see it at a certain scale, as Gia said. So the best test of it right now is done by my UF colleague, Dmitry Burlikov, and that's measurement of the electron structure function, point-like, and there's a prediction in QED for what it should look like. And if you see deviations from that, then you're seeing non-point-like structure. And so far they haven't, down to, I think it's 10 to the minus 19.
Yeah, it's pretty accurate.
Yeah, it's hugely.
10 to the minus 19.
Yes.
Centimeter. Well,
yes,
it makes a difference, doesn't it?
Yeah, 10 to the minus.
And I'm sorry, I don't remember whether it's meters or centimeters, but it's not the Planck length. It's not the Planck scale yet. Or even close.
And we remind that also in your theory, you have a kind of effective theory that you can compare with quantum field theory.
Could I make a comment, though, in answer to the question that the gentleman in red there asked? I don't know what your name is, sir.
Clario.
Paganini. Clario. So I don't know about discretization, except what the point that Gia brought up, but there is, I think the most notable thing about your class of theories is not the discretization, but the possibility of topology change. And I think there would be ways, not definitive ways of saying that there either is or isn't topology change, but if there was topology change, I think we could do, I think there are observations that would show it like, would stick out like a sore thumb. Like, for example, a sort of a garden variety of topology would be that topology change would be that these 2 points, which right now I think are different, suddenly become identified with each other. If that occurred, you would see flashes of light. You could see things that look like acausal propagation. If it occurred in cosmological scales, you would see, situations where a quasar went off somewhere and somewhere else you saw the light that was clearly from it coming out. We don't yet see anything like that. So that probably puts some limit on the ability of that kind of stuff to happen, but it doesn't, of course, you can't ever rule it out by observations. But that would be, I think that's the sort of most...
that topology change would be there in any non-perturbative theory, or many non-perturbative theories might want to sum over topologies But those are phenomena that would happen at very early universe or at very, very small scale. So fluctuations in topology would happen at very small, and there are fluctuations here as well. So even if you have a continuum spacetime, in the very small, there'll be fluctuations.
So it ought to be,
Back to the gravitational field.
it ought to be possible then to make a.
Also, Philip, which is waiting from.
Oh, sure, of course. Sorry.
Are you there?
Yes, hello, hi, good afternoon, everyone. I wanted to make a few comments, mainly about the questions on the screen. But before I do that, let me just go back to the discretization question. Gia asked, if it is discrete, is it useful? And as opposed to, is it interesting? And Richard asked the reverse question, what would go wrong if space-time is discrete? Which I think is a very crucial question. But I'd like to ask a different question. What would go wrong if space-time is not discrete? And I think that's the people that are on the discrete side really have to answer. What would necessarily go wrong? What would be bad if somehow space-time was not discrete? And that I think is the open question. Now, regarding the questions on the screen, do we really need quantum gravity? It really boils down to, do you accept Einstein's argument that everything gravitates? Is it possible that there is something that doesn't gravitate? If you agree that everything does, then basically you're going to be forced to quantum gravity for the following reason. You write the Einstein equations, Einstein tensor equals energy momentum tensor. Keep the Einstein tensor classical. We know that the energy momentum tensor is absolutely quantum mechanical. So what you then do is you replace the energy momentum tensor by a C-number matrix element. But the C-number matrix element contains a product of fields at the same point, and therefore it has a 0 point infinity. So you subtract off that 0 point infinity, and then you finish up with classical Einstein gravity equals normal ordered matrix element of the energy momentum tensor. Now, if you do that, you are claiming that the 0 point of matter does not gravitate. And therefore, you're basically denying the hallmark of Einstein gravity. On the other hand, if the 0 point of matter does gravitate, then you're going to need on the gravity side a 0 point of gravity which can cancel the 0 point of matter. So once you write down the Einstein equations, it seems to me you're basically forced to quantum gravity. Now, what kind of quantum gravity theory could you possibly consider? Well, right at the beginning, the chairman of the session noted that there's an issue about the fact that Einstein gravity is not renormalizable, whereas SU3 cross SU2 cross U1 is. So now you should really ask is, why is 3 cross 2 cross 1 normalizable? And the answer, renormalizable, and the answer is because it has dimensionless coupling constants, and at the level of the Lagrangian, it's conformal invariant. Now, if gravity is to be equal to this theory, which is conformal invariant at the level of the Lagrangian, then gravity has to be a conformal invariant theory too. Now, I won't say a lot about quantum gravity, that's about conformal gravity, that's what I work on. But point 3, it's renormalizable. It's, you have another question, is it unitary? Where Carl Bender and I have shown the theory is unitary. And does it have a standard classical macroscopic limit? And the answer to that is yes, that I've also shown. So it's a perfectly viable theory. And going down to point 6, it eliminates the need for dark matter or dark energy. Point 4, the proposal is not fundamentally discrete. It's a perfectly continuum theory. So that's what I believe I answer all of the points. The question 5, how to discriminate between continuum and discrete, theoretically, I believe, is to take a gravitational wave interferometer with a double slit, and you either see the maxima and minima on the screen that you would have got from the continuum theory, or you see something different. So a gravitational analog of the double slit experiment would, I think, in the end, provide a theoretical discrimination. Those are my comments.
Thank you. Thank you. I don't know, maybe you had more follow-up.
Actually, it was a follow-up to Claudio's question.
Okay.
So what I think is that whereas in principle you can imagine that some experiments could establish that space or space-time is discrete, I think that there cannot be any experiment which establishes that space-time is continuous, because you can measure things only with a certain resolution. If you measure that everything is continuous at that resolution, it doesn't exclude that it is discrete at some lower resolution.
Well, okay, but like if we could show that it's continuous on the Planck scale, then I think most people would agree that it's continuous.
Well, I think continuous is always, as has already been said, up to a certain scale. And so you can never establish that it is continuous.
I'd like to extend the question and pose it to Surya. In theories with topology change, you ought to be able to make some prediction for phenomena that fascinate me personally, like, for example, superluminal propagation. Maybe it's a very small effect, but it ought to be occurring. If fluctuations in topology are occurring, it ought to be possible for things to choose paths that take that fluctuation and get there faster. So we ought to be able to do experiments like my old physics lab, Professor Crouch used to do under Lake Erie, where you set off an explosion and then you try and measure a pulse later on, but out of but space-like separated from it. There maybe the result, maybe the prediction is way too small, but I would urge you to do it, to get your money in on it, because maybe they'll see such an effect.
When you're thinking of wormholes and
yeah, fluctuations in topology could allow that kind of stuff to occur, and
I mean,
it must be occurring if your theory is right at some level, and it would be very interesting to make a prediction to see what the prediction is for the amplitude that we should do. So, for example, if we set off a pulse of, a certain magnitude and energy, what fraction of or if we set off a pulse of 1 billion photons, what fraction, probably far less than one, would arrive at the detector before the light time lag?
I would say that you need a theory of quantum gravity, which will allow you to calculate these amplitudes.
You have, say, opening up.
No, I understand, but would not that violate causality?
Yes, it would. It would violate causality of the flat space that we're
Yeah, it would violate the causality of the flat space, but basically what you're doing is you're summing over, and each of them is a Lorentzian geometry, hopefully. I mean, each of them has got a internal causality, and you're superposing. And so I would ask, even in perturbative theories, where you're going off flat space, you would still have some kind of quote-unquote violation, because you're summing over
I did make such a prediction.
Right, so,
I'd love to see it in your theory,
but
too.
This isn't fully you can't have topology change in a perturbative theory. It's going to be a non-perturbative.
Topology change, you can't happen, but you mentioned that you can have fluctuations a little bit outside the light cone, and indeed you can, because derivative interactions will push you a little bit outside the light cone. And Katie Leonard and I did do that calculation. It's a very, very small effect. In your theory, it ought to be occurring due to topology change. And I would urge you to
topology change, because for us, I mean, when you talk about topology change, you're really talking about continuum structures. I mean, I have been interested in topology change in the past when I worked in the continuum theory, but not now, because here everything is a discrete structure. We will look for fluctuations in the discrete structure, which will be fluctuations
in continuum, but paths opening up between 2 points that are
Yeah,
not
so,
causally related in the average geometry, you ought to be able to make
but
some
that's a
prediction for what
non-perturbative
that.
effect in anything that you're doing. I mean, that if
No,
you
no,
have
no, it's
topology change,
a completely perturbative effect
you
in
can't create,
quantum
you can't
gravity.
create, I mean, in quantum gravity, if you're going to do a sum over topologies, that's a non-perturbative effect.
Not due to topologies. There's a completely perturbative effect in quantum gravity where derivative interactions push you a little bit outside the light cone.
Okay, yeah, that's
It's called the
fine.
blurring of the light cone. It was talked about by Oscar Klein actually here, I guess, a long, long time ago, before any of us were born, before even I was born. And it should be true. It must be occurring at some level. In your theory, there must be another effect which is causing this to occur. It's probably very, very small, but I would urge you to do the calculation to get your marker in now, because who knows,
Well, I
maybe it's
mean,
right.
so what I can say is that just as you have summations over different causal structures, you can also do that, but you'd have to look at the contribution from things that are fluctuations about flat spacetime, for example, or a fixed spacetime background, and we can look at those fluctuations and to evaluate that path integral in some nice way. You're looking at fluctuations about very large number of points. This is not an easy calculation, even on the computer. And this is why even to show these, these saddle point approximations.
Why they give out Nobel Prizes for the first people to do things.
Yeah, but you see, I'm in Sweden for different reasons. This is not the motivation, right? I mean, so the point being that this partition function that you want to calculate, so it would be very nice to be able to see what are the fluctuations about continuum spacetime. So you look at things that are close, like you do, but on this discrete structure, which is a sum over, partition function that you can write down. So in that, if you calculated observables, which we can do in principle, but to do that sum, that full Lorentzian sum, that full, oscillatory sum, is not an easy thing on a coset. So these are not nicely structured lattices. You can't do it in QCD. You have to go to the Euclidean sector. To do it in quantum gravity is not an easy question, but I think it's an interesting class of questions one can try to do some kind of simulations for, or try to answer in some kind of.
Wouldn't that be an even bigger problem than what you said? If you violate causality, I don't understand.
No, they're positing that topology change occurs, and if you had topology change occurring, it could happen. It wouldn't violate microcausality anyway. It would be saying that there's an opening from here to there. That could happen.
That's a non-perturbative effect. I will still say that's not.
People used to talk about that in these theories of third quantization. You're old enough to remember that, right? From Coleman.
I remember, but I think the conclusion was that the causality should not be violated, even at a microscopic level. But maybe.
Well, at a microscopic level, yeah, it shouldn't be. But at a global level, a global topology change, I think it could occur. I don't think there's any theorem that says it can.
I mean, if you superpose two different causal structures that are very different, and you said, I have a quantum state, which is a superposition of two different causal structures, then with respect to one of them, you will, if you actually have some focus on the other one, you could violate, in some effective sense, but you would have to define that very carefully. But I think that's the sense in which we're talking about causality violation, but not, with respect to some effective single geometry with, whose causal structure it's violating. But there's no violation of causality in the individual spacetimes that you have. It's just that when you put them together, you could have some.
I'm worried about causality in the spacetime that I live. So I think if theory would violate causality in this spacetime, for me it would be a disaster. But I don't know, maybe you're saying it's okay.
But it's not one single spacetime in quantum gravity, right? I mean, we live in superpositions.
If it occurred due to topology change, I wouldn't have any objection to it. It might be a problem or not. But it doesn't seem to me like it's a fundamental problem.
But Richard, I don't think you want to have 6 fingers now.
I definitely don't.
Yeah, to me
it's a topology change effect. Or 4.
Yeah, it would be a weird universe, but it might be occurring at some very, very small level. I don't know. I mean, we see things in the early universe that could be explained either by primordial inflation or by acausal correlations. Maybe there really are acausal correlations. I don't know.
Please.
If I go back to the original objection raised by Richard with the expansion of the discrete discretization of quantum gravity, okay, one can ask the same question without quantum gravity. So the base of the argument basically was that what was the growth of the scale factor by a factor of e to the power 120?
Yeah, it would apply equally well. There wouldn't be the motivation for discretization. So I imposed the Planck scale as the scale of discretization because I was saying, okay, suppose that you want to usefully solve the ultraviolet problem in quantum gravity, then you need to keep quantum effects small. That means you need the cutoff to be, in terms of the physical length, to be bigger than the Planck length. But that's how it came there. But you could say the same thing for a matter theory too.
Exactly. So let's forget about quantum gravity. So take any scale in today's universe. Sometime in the past, it was Planck length.
Sure. Yes, absolutely. We believe so.
Most of the scales in the universe have emerged from sub-Planckian scales.
Yes.
How do we understand it? Because sub-Planckian...
We don't understand it very well. That's called the trans-Planckian problem. And we don't understand it very well. And to me, everybody says, you know, that in the primordial power spectra, we have a very nice formula for the approximate formula for the primordial power spectra in terms of the expansion history of the universe. And everybody says, well, you know, suppose we had a glitch in the potential or something. Those are infinitesimally small effects. The biggest effect by far is suppose the universe was not in perfect Bunch-Davies vacuum at the beginning of inflation. And why should it have been? Well, nobody knows. There's a speculation. It's what Weinberg would have called a folk theorem that somehow evolution from the trans-Planckian region to the sub-Planckian region leaves the various modes of the theories that we're used to, like massless minimally coupled scalar and the graviton in Bunch-Davies vacuum, but nobody has proven that. Nobody even has the ability, the technology to prove it, and it's just an unsupported belief. And if you weren't in Bunch-Davies vacuum, you can change the power spectrum, the prediction for the power spectrum by a density factor that could go all the way from 0 to infinity. That's the biggest effect in our uncertainty of that, and we don't understand it.
So if quantum gravity people can give us some formula which they derive in a consistent way, then we will be happy with it.
Oh, amen to that.
Understand
and I would go further. I would say that the discussion, I don't really understand the focus of the quantum gravity community. If I were looking at it, I would say that today the people here are focused on the ultraviolet issue, most of them. And most of the people who aren't here are focused on the black hole information problem. And I really don't understand why. I mean, we have 0 pieces of information about that, no data at all about black hole evaporation. No, we might eventually find a black hole that's nearly evaporating and build a starship and go there in 100 years, but it's not going to happen anytime soon. And in the meantime, we have 10 to the 7th pixels of very high quality data on the scalar power spectrum with a potential expansion up to 10 to the 16th if 21 centimeter cosmology comes in as it might, and we're just ignoring that. And it's just exactly what you say. I mean, there is gold there. If we could, that's our bailiwick, that's quantum gravity. If we could resolve that and come up with an explanation for why that's true and make a unique prediction, and people are just uninterested. It's just like it doesn't exist. It's not even a problem. I really don't understand it. I think in the future that will be looked back on as one of the great blind spots of the theoretical physics community, but maybe I'm wrong about that too.
But it is a UV problem, right? That one, because you said that
it's in that peculiar region of UV goes to infrared. So It's what happens as something goes from the Planck scale, where everybody admits we lose control, to say 10 to the 16th or 10 to the 14th GeV, something like that, in a region where we might possibly be able to do calculations. And I cannot believe that people are making array predictions about what happens in the last moments of black hole evaporation and worrying about things that we can't measure in the ultraviolet problem. And there's this huge glaring problem, and it's our expertise that could solve it, and we're just ignoring it.
Let me understand what you call a problem. I mean, so let's say today, let's assume today are in this sector, and let's tag a graviton that got created today.
Let me say it in words there. I think we're not focusing on
So
I'm talking about this formula right here. That this is approximately equal to G times the Hubble parameter at horizon crossing over pi epsilon of T. That's an approximate formula. That's the WKB approximation.
You didn't let me finish my question. The question was.
But you were raising the issue of what I was talking about, and what I'm talking about is that all issues about what happens if you improve the WKB approximation are completely subdominant to what happens if this is not in Bunch-Davies vacuum.
No, it would be, of course. I mean, one thing is to of course improve computations and stuff, but I mean, again, if we come back to this, let's say today we are in the center. Let's assume we're in the center, and then a graviton got created today as a quantum fluctuation. It has a huge wavelength, and then this graviton keeps redshifting, and then down the line, I don't know, our future generations, if they're still left, so they detect this graviton, and now they say, okay, this graviton now has this wavelength. Let's rewind it to the Planckian length. But that would be a fictitious problem because this graviton was created when it was huge. It never had a Planckian length. So where is the problem there?
The problem is that there's a stimulated emission effect in the creation of these particles. So you're saying that, gosh, that thing is not being caused from the beginning of the universe. It's being caused by creation of the stuff that occurred during inflation.
Exactly.
You're right about that, but there's a stimulated emission effect that goes that if the thing was not in Bunch-Davies vacuum, then this thing can get multiplied by a factor.
No, that I fully agree.
Here, which can go all the way from 0 to infinity.
I mean,
and can depend arbitrarily on the 3 momentum.
No, infinity, I don't know. I mean, I fully agree that. No, I fully agree that it's very interesting.
You can write down what the state would be to have it go to infinity.
No, I agree that it's interesting to explore what are the corrections from the shorter wavelengths and maybe, but I don't see a problem. Because problem is you don't know whether these gravitons. First of all, you don't know how to compute gravitons that are creation of gravitons that are shorter than Planck length. You don't have simply calculation tools. We don't know that.
I agree with you. You said it right at first. These things are not being created at the Planck length. They're being created at cosmological scales. They're being created at horizon scales, so they should be sub-Planckian. There should be things that we can control with quantum gravity. The problem is that there's a stimulated emission effect, so that the rate at which things are created is different depending upon which state they start out in. So if it's not in vacuum, if it's in vacuum, you get one thing. That if it's not quite in vacuum, if there's one graviton around, it's a little bit different. 2, it's different yet. 3, it's different, and that uncertainty, the uncertainty of what state it was in when you started out inflation, is dwarfing into insignificance the effect that's only an approximate formula.
No, it's a very important question, but I don't see a problem. This is what I'm trying to say.
The problem is that we lose predictability, so that even if somebody told us, if the beta reticulans came down and said, look, we've been thinking about inflation for 1 billion years and we know that the model is this, it wouldn't matter. We still wouldn't be able to predict what, if we had the exact scalar potential or whatever it is that's driving inflation, we still wouldn't be able to predict what the scalar power spectrum was, or for that matter, what the tensor power spectrum is, without knowing what state the the particles were in when the particle production occurred.
Sure, we don't. No, that's absolutely correct. We lose predictivity because we don't know how.
That's a terrible problem.
But
right?
normally there are good arguments. At least this is what people say. That's why you are angry at them, because they ignore the problem. But usually, I'm probably one of those. But usually they.
You're one of the most phenomenological quantum gravity people. But anyway.
Anyway, but usually the assumption is that yes, we lose predictivity beyond certain wavelengths, but we assume that contributions from those wavelengths are not so important for the effect. But of course, I fully agree that it's a precision physics.
But this is stuff we can measure.
Oh no,
we can
that
measure.
part I fully agree. That's very
interesting. And I'd love to be able to. I mean, the late Alexei Starobinsky is not with us any longer now. But suppose we wanted to confirm R plus R squared inflation, up to this ambiguity, we could do it. But with that ambiguity, we can't.
So just to say that. If we don't know the theory of quantum gravity that's going to give us that, we don't have a well-defined formulation. Shouldn't we be working on that well-defined formulation? Of course, we would love, I think any theory of quantum gravity would love to be able to make connections.
Well,
phenomenology, but to define things carefully, we have to spend a lot of time and effort trying to define things carefully. Otherwise, it's just going to be another model, which is no different from inflation, which is not going to give you fundamental reasons for something to happen. I just want to say, so maybe what we're looking at is a time where, yes, there's loads of data, but also there's not enough theoretical understanding.
But there is. See, that's a completely reliable prediction. Once you start with a fixed initial state, it's in the regime where effective field theory should be correct. It's in a regime where we don't need to know the full quantum gravity theory. We don't need to know how it resolves the ultraviolet problem.
So then you don't need to know how Planck effects are coming to this. I thought that was a question.
We need to know how Planck effects are setting up the initial state. But once the initial state is set up, we can make the calculation completely reliably.
To me, that sort of maybe to me just sounds like which comes first, the chicken or the egg, because it sounds to me that you need to know what you're predicting. I mean, you need to have a theory to be able to predict something. And if you don't have that theory, then we're going to go back to doing things that people do in inflation, which is to make up potentials, which is a great thing to do. It's a good phenomenological point of view, but where does it come? If you really want to know where it's coming from, I think you need to spend time, and maybe it's just the historical time that we're disproportionately less in theory than in observation.
Well,
I mean,
maybe we're not,
I think it's okay. I think it's all right. Sociologically, I think
agreeing on the scales here. So if we draw an energy scale, right, up here at 10 to the 19th GeV, I agree, we don't know anything. We can't calculate reliably here, but inflation is happening below 10 to the 16th GeV, maybe 10 to the 14th GeV, we don't know. And the issue is, as modes propagate from the Transplanckian region into this, is there some mechanism that would cause them always to be, no matter what they started out in, always to be plopped out into Bunch-Davies vacuum? It's Bunch-Davies vacuum that's giving us that prediction. And once we get to this point and we know the state that we're starting from, we can make a reliable prediction for what the power spectrum is. That's not.
But you are asking for that transition, and all I'm saying is that you have to be able to know what 10 to the 19 GeV physics is before you're able to say it's going to lead to this 10 to the 16 GeV physics. I mean, I'm just saying something obvious, and I think we just don't have that theory. I don't think we have that theory. I mean, unless somebody does, we are done.
I'm not sure to remember correctly, but one way to rephrase this problem is to say that all the higher order operators do not change this Bunch-Davies state.
That's right. Whether there's C squared,
proposal could be an asymptotic
R squared, all of that, VPHC. You can see it when you look at the amplitude for particle production. I think I remember it. It's a staggering number. The occupation number is K dependent, and it's approximately if I remember it correctly, it's AH over 2K squared. That's the scale factor, which in de Sitter is growing like e to the h. And that's the thing that tells you you can calculate these things completely reliably, because it only becomes of order 1 when the physical scale, that's K over A, is comparable to the Hubble radius. In other words, when it's cosmological scale, what that tells you is you can use Einstein-Hilbert as completely reliably as an effective field theory. And it's growing like a staggering amount, and it wouldn't matter. This is, ultraviolet divergences don't matter. That would just be a finite R squared or C squared counter term. This is coming from the non-local and infrared, ultraviolet finite part of the theory. It's a completely reliable prediction of the theory, and the question is whether we can identify some mechanism in this in-between region from where we certainly have lost control at the Planck scale to the 10 to the 16th, where we can come up with some mechanism about why it is that the universe seems to be putting the particles, the various mode by mode by mode, plumping them into Bluntsch-Davies vacuum. Because if it wasn't, we wouldn't even see, those beautiful curves that we see. We wouldn't see that. If it was putting them in arbitrary states, it would all be, waved out. We see something that's smooth. It must be somehow putting them into Bluntsch-Davies vacuum. And I just can't believe that people in the quantum gravity community are not interested in trying to figure out why that's happening. It seems to me like that's our natural expertise. The cosmologists are never going to do this. This is something that we should be thinking about. And anyway, I've already said what I think.
Yes, please.
So I think around 20 years ago, Ulf Danielsson from Uppsala, our neighboring university, he did something in that spirit, where he considered a situation where the initial state is not Bluntsch-Davies, but some other generic state. And then the effects apparently are of the order of like h squared by Planck mass squared. So they're not really observable.
Is there a tendency, did he find a tendency to put you into Bluntsch-Davies vacuum if you started in some excited state?
So essentially, the deviations that you would see from Bluntsch-Davies is of order of h squared by m Planck.
I see. He found that no matter what you started from, it would always be a small deviation from Bluntsch-Davies.
Yeah.
That's the result we want.
Yeah, but the actual
That's what the data is telling us.
But the actual analysis is kind of it gives you the result, but it's not fully satisfactory because you have to assume some kind of constant mode creation about which you don't know. And moreover, the mode creations are done at fixed energy, not at a fixed time. So technically, it's difficult to analyze. So somehow it seems that what Sumati says that at the end of the day, you need some kind of understanding of quantum gravity to.
Well, I would say this is a quantum gravitational effect, by the way, the first ever observed, and
yeah, I mean, high energy
at Planck scales.
Yeah, Planck scale, yeah.
But let's think about it, right? Even during inflation, it's a very, very small effect. The loop counting parameter in quantum gravity, which measures how small quantum effects are, is very small. This is like 10 to the minus 10, hugely better. A factor of 5, the power of 5 better than QED. It ought to be that it's very, very reliable to do quantum gravitational calculations here. Now, we lose it as it gets closer and closer and closer to here, but then the question is, how quickly do we lose it? And is there some way that we can gain some understanding? If there was even a mechanism that kicked in at 10 to the 18th, where we still had perturbative control, and would say, how it is that we wind up always in Bluntsch-Davies vacuum or pretty close to it. So that is an awesome result, and one that we ought to be getting.
If you assume 60-fold inflation or more than 60-fold inflation, then essentially probably you are starting close to Planck scale.
Oh, absolutely. Yes, sure. That's called the Transplanckian problem. It has a name in the literature. It's called the Transplanckian problem. And usually it's said by what you said that there has to be this mode creation. I would say that there always were the modes. And the real issue, and there's modes all the way up, even if there's 10 to the 10 e-foldings of inflation. And the real issue is why it is that no matter what they come in, what they came down from the ultraviolet to, why is it by the time they reach the point where inflationary particle production occurs, they're pretty close to Bunch-Davies vacuum, which is what the data is telling us. Those beautiful curves that you see of the CMB fluctuations wouldn't be there. They'd be all washed out by fluctuations like that. You'd see noise in it, but you wouldn't see the beautiful smooth curves that we see.
But do you think you need to go beyond Einstein's theory, or you would like to solve the problem in the Einstein?
Since I haven't solved it, I really don't know. My guess is that Einstein's theory, considered as an effective field theory, would be an explanation of it. But you know, I mean, I don't honestly know how to solve it. What we want is something like what that gentleman there mentioned that Ulf Danielsson did, where you use Einstein's theory or whatever as an effective field theory, and then you show that there's a mechanism in that theory where higher order interactions tend to force a state which isn't initially in Bunch-Davies vacuum down to Bunch-Davies vacuum by the time it reaches the point where inflationary particle production occurs.
Okay, but there are other questions.
So this panel is forever? Or?
I hope not.
I think it's time.
Sorry,
After this comment,
I don't want
time.
to interrupt, but
No, not
But we can rescale it, you know, cosmologically.
No,
We're
we're
expanding.
supposed to end half hour ago.
okay.
Okay, so it's time to thank you everybody for coming. Thank you to the